So in the previous video, we looked at potential energy, right? We understood that potential energy is the energy of a body by virtue of its state or by virtue of its configuration in a system, right? The first type of potential energy we looked at was gravitational potential energy, and we saw the gravitational potential of a body is given by mgx, where x is the displacement. Now we're coming to the second type of potential energy, and this energy we have found this energy thanks to the renowned scientist Robert Hooke, right? And this energy, potential energy, is called elastic potential energy. It's very common that all of us has worked with a spring, right? We pulled a spring or compressed a spring, stretched it or compressed it. I mean, something that we have done. Now, what happens is, let's say, consider a spring over here and a body attached to it. In its state of equilibrium, the body, let's say, is x is equal to 0, or the spring is at x is equal to 0. When we say state of equilibrium, we mean neither stretched nor compressed, right? Now, I pull the body, towards the right. That is, I stretch the spring such that the displacement, or this, I stretch the spring by a distance x, right? The moment I stretch the spring, I feel a force, right, which we call the spring force acting in this direction, right? And a work is done to stretch this. Obviously, a work is done to stretch this spring. So the question here is, what is that force? How do you derive the force which is acting when you stretch a spring, right? Robert Hooke would derive the force for that, and he would use an anagram. So he would first put it as a puzzle. It was a very interesting way in which he would put this across. He would first put an anagram as a puzzle, and then he himself would solve the anagram, and he would say, "Intensio sic vis," okay, which means as the extension, so the force, right? Or in other words, what he meant is the force acting is directly proportional to the extension or the displacement of the spring, the distance the spring is stretched, or F is proportional to x. In other words, so the equality symbol is given by F is equal to minus kx. Okay, and this would be known as Hooke's law, right? Now, what is k? The constant. The k is known as spring constant. So that is specific to this spring, right? It's a spring constant. And what would be changing is the displacement, or the extension, and the force is changing, right? The more you displace the spring, the more would be the force, and it would be a directly proportional relationship, right? So similarly, if you were to compress the spring, okay, so by compress the spring, by push the spring into, and therefore the body is somewhere, once again, let's say a displacement, this was a displacement to the right, let's say it had a displacement towards the left, then you would see the force acting would be in this direction, right? There would be a force F acting in this direction. And what you would see here is that, again, the displacement is in this direction, force is in the direction, F is equal to minus kx, still makes sense, right? Now, as we said, right now we are studying to understand what is the potential energy, because as we said, when the body is stretched, the spring is stretched, work is done. This work is stored in the spring system as as elastic potential energy, right? So now we need to calculate what is the potential energy. Now let's say we stretch the body by x, by a displacement x, by a distance x. What is the potential energy stored in the spring system? How do we do that? We've already seen work. We know work is equal to integral f dot dx, okay? And I'm going to put it as ds. This is the displacement. It's a dot product, right? So the cos theta, the angle between the force and the displacement. So in this case, we know that the force is kx, we already saw that. And it's moved by a distance dx. We are integrating over an infinitesimally small distance dx. The angle between the displacement and the force we saw is an opposite. Displacement is in that direction, force is in this direction. So it's a cos 180, so it's minus in this case, so I put a minus sign over here, and I integrate, let's say, from the equilibrium position to x, so 0 to x position I integrated, right? This is a simple integral, so it's going to be if you integrate x squared by 2, putting in the limits 0 to x, you get minus half k x squared. Right. This will be the work done to extend it by a displacement x. Right. Now, this work done by the spring force is stored in the system as elastic potential energy. Now, we know that the potential energy is equal to, which we are representing as delta U over here, is equal to minus of W, okay? Minus of the work done by the conservative force. Now keep in mind that the force, the spring force, is just like the gravitational force. Spring force is a conservative force, right? It depends only on the initial and the final position of the body, right? It does not depend on the path of the body. Anyway, so since it is a conservative force, we know that delta U is equal to minus W, the potential energy, and this is equal to half k x squared, right? So the potential energy, I always keep saying electrostatic, the elastic potential energy for this body is given by half k x squared. A little more of a simple derivation, which you should know is, let's say I stretch this thing from a position I to, that is x is equal to I, and then I stretch it to x is equal to f, right, which is the final position. Remember, the stretching and compressing, it remains the same, right? The elastic potential energy remains the same. So let's say I stretch it from initial position is at I, and the final position is f. We do the same thing, and you would get that the potential energy, potential energy would be equal to half k x final square minus half k x I square. Okay. So the potential energy at the total potential energy, the final position minus the potential energy will at the initial position will be the change in potential energy of the spring system.